I've got another chink in the puzzle. I knew these diodes had something to do with what's going on here. I am using this capacitor as if it were a piezoelectric crystal, quartz crystal. I'm causing it to vibrate. Why is that? Because I'm squeezing it with voltage by building up voltage on one side coming from these diodes. And that causes the frequency, it causes this capacitor to start to vibrate. Now normally it wouldn't do that because we're simply building up charge and we're not allowing it to discharge. Yet we're squeezing it by increasing a voltage beyond, probably, I'm speculating, probably beyond what it would normally carry. Normally I would suspect that something of such a low value, because normally I'd go higher, but apparently I had to go lower to get this thing to work. You know, I'm normally at 10 nanofarads for all of my capacitors, but I had to reduce this to a picofarad. So normally a picofarad capacitor probably doesn't store 450 volts. I believe, if I'm not mistaken, I have a lot of voltage building up there. Let's see if I can find the... Now I'm curious. I want to go find the picture. Where did I put it? 100 milliseconds. No, that's the inductive load. Well, let's see. Nope, not that one. No, not those. Oh, the inductive load, yes. Okay. The resistive load, inductive load. So, since this is a reading of the load 3, well, it used to be called load 3, now I've renamed it load 2, because this is not a load, this is a buffer. This has to stay there. So now load 3 becomes load 2. So the inductive load here is adjacent to the capacitor, and so its voltage, along with the voltage of the transformer, you know, they run in parallel, so we can use this as a guide here. So the voltage escalates at around, I don't know, it looks like maybe 50 milliseconds or whatever that is. It quickly rises, and then it plateaus somewhere in the vicinity of around 400 volts. And then the amperage, of course, rises very gradually. So, whoops. So, it could be we're compressing this beyond its normal capacity to hold a charge, you know, because we're not allowing it to release. You see, a normal tank circuit, the capacitor is free to discharge and charge. Isn't that the case? You know, let's go get a little tank circuit here. Let's go get a... Alright, so we give a capacitor a charge, and a capacitor coupled with an inductor. We charge it up, we release it, so that it's free to oscillate at its own resonant frequency. And of course it dies out, right? Because we got this resistor in the way. Let's charge it up again. So now let's charge it up some more. So what do we got here? We got the resistor. We don't want to look at that. We're looking at the capacitor and the inductor. And we don't really need to look at the capacitor, but let's look at it anyway. So now they're free to oscillate. And, you know, we'd expect that's what would happen under normal circumstances. This is what we would expect. And eventually it'll slowly die out depending on the resistance in the circuit. Okay? So this is what's normal. Normal behavior. But then we go over to this. This is not normal behavior. You know, the voltage rises. So I think what's going on here is that the use of diodes shoving voltage over to a capacitor, you know, in a DC fashion. You know, the input is AC and the output is DC before it leads to the capacitor, of course, is very unconventional, but we're squeezing the dielectric of a capacitor. And then it starts functioning like a piezoelectric quartz crystal. And so now it starts to vibrate. And guess what? When we look at, what is it? Oh, I love gas laws, finally. There's no charts. I love charts. That doesn't look like a chart. References. Well, let's see. What does it say? The gas law was developed at the end of... I gotta read this. Like, it's too tiny. At the end of the 18th century, when scientists began to realize that relationships between pressure, volume, and temperature of a sample of gas could be obtained, which would hold to approximation for all gases. Gases behave in a similar way over a wide variety of conditions because they all have molecules which are widely spaced, and the equation of state for an ideal gas is derived from kinetic theory. The earlier gas laws are now considered as special cases of the ideal gas equation, with one or more variables held constant. Oh, so this is thermodynamics of an isotherms of an ideal gas. Pressure, the most frequently introduced form is... Yeah, that looks like, this looks like it. So it's the ideal gas law, is what it is. Oh, here's this again. Avogadro. Oh. Boyles, Charles, Gay-Lussac, Avogadro combined ideal gas law with the Boltzmann constant. Oh, now we're getting somewhere. Boltzmann constant. Now what's that all about? Physical constant named after its discoverer, Ludwig Boltzmann, which relates the average relative kinetic energy of particles in a gas with the temperature of the gas, and occurs in Planck's law of black body radiation and in Boltzmann's entropy formula. Ooh, we'll just stick with this. Boltzmann constant. So anyway, it has to do with this stuff. So here we are, and what was the point? We're pressurizing this capacitor with voltage. See, we don't have to do Tesla's special, what was it, that patent on pressurizing a capacitor, because we're not trying to change its equivalent series resistance. This thing over here. We're not trying to, of the dielectric, we're not trying to do that. Yet we are. Well, at least, oh my God, not by applying mechanical pressure, but by applying voltage pressure, if we can call voltage pressure. I don't know. Most people do, but sometimes I get other opinions. For the moment, let's just call it that. So we're applying voltage, which, as far as piezoelectric crystals go, is equivalent to pressure. And that's probably why people talk about voltage and pressure in electrodynamic theory as equivalent or parallel terms anyway, because piezoelectric crystals work that way. So we pressurize the capacitor with voltage, and it starts ringing beyond what it normally would oscillate at, because the voltage is going up higher than what it would normally carry. And because of this relationship, we raise the temperature, you know, we raise the pressure, the frequency. Ah, the frequency. That's the kinetic energy of the particles of a gas, right? That's the frequency, the kinetic energy. So we've raised the kinetic energy of this little capacitor simply by pressurizing it, and that raises its frequency. Got it. That's why this system escalates. I knew it had to do with this capacitor and the diodes. I just couldn't figure out why. Because we're pressurizing it beyond its normal ability to carry a charge, and disallowing it to discharge. You would think it's going to try, you know? The voltage keeps coming in, and it's going, no, no, I want to release, I want to release. And it keeps coming in, no, no, you got to take more, you got to take more. Sorry, my falsetto broke there. And so it keeps trying to release. Right there, we've got oscillations right there. And the more it gets pressurized, the more quickly it tries to get rid of those buildup of voltage, because it's being pressured to do so at an ever increasing rate up to a certain point, you know, and it can't increase its pressure anymore because it can't hold it anymore. Well, I don't let it. Ah, see? That's why, because I don't let it. You see, this is why this goes up and then all of a sudden stops. You know why? Because this is the very first surge, or the very first spark gap release. Where can we find a graph? Nope, wrong direction. Here, no, here. So we have this at, it looks like, well, if we divide 53, let's see, 53 minus 42 is 11. So I'd say that's around 45 milliseconds, which looks like, for the first release, it looks like that's about correct, because this line here is 200 milliseconds. So that would be 100 right here, and that would be 50. That sounds about right. Somewhere in the 40 range here, 40 milliseconds. So at 40 milliseconds, this stops surging and then begins to plateau, only because of the spark gap is now firing, because this capacitor did its job and is free to oscillate, unlike this one over here, and dumps its charge and says, hey, look, it's time to, we've got enough voltage difference between the two sides of this capacitor in parallel to the two sides of the spark gap. It's time you fire already. And when it fires, it realigns the current with the voltage so that the surge can stop surging. Now, I still don't understand why the voltage and the amperage separate by half a cycle, but at least now I can see why the frequency goes up, because I don't have, let's see if I can find for you the graphic image that shows the escalations. This is so fascinating. I had a slow build up. Whoopsie. Let's see, I've got so many images here. You know, I don't think it's here. I have to go to another place to find it. I'll just go through here. Maybe we'll... Whoa, what was that? Ah, here we go. 10 microsecond duration of a surge developing from a 2 megahertz input frequency. So I created circumstances to try to elevate the conditions so we can see that the frequency is definitely increasing. We start out with... See, this was a complaint over at Stack Exchange. Well, all we see are, you know, what I showed you earlier, which I won't go fetch because it took so long to get here. Triangular waves. No, they're not triangular waves. The simulator can't catch up, can't keep up with the increasing frequency, and so all I can do is approximate a sine wave by the use of drawing it as a triangular wave. But you can see right here, this looks like pretty close to the curvature of a sine wave, and then it increasingly becomes more like a very jaggedy, whatchamacallit, triangular wave. Okay, so here we've got the voltage separated from the amperage. Oh, there's a good example of noise. The blue is the current, and the red is the... what is the red? Oh, the RMS of the current. So the blue is the raw current, and the red is the RMS of the current. And that's what comes out of the sine wave generator. In this case, it's a third of a nanoamp, which is feeding this circuit, this particular example that is somewhere. It's up here. It's this thing up here. Is it this one? Yeah, maybe. Let's see. Let's expand this to find out for sure. Oh no, this was the special case where I rectify it to create a little DC condition over here. So we had 50,000 hertz, and that's where that came from. So see, I have 10 farads here in this capacitor, and 1 nanofarad over here adjacent to the spark gap. So it varies, you know, depending on what you do, what you try to do. Anywho, here we go. This is it. But I put them all together, but they are separate. So here's 50 microseconds duration. Oh, it's going backwards. So we're going backwards here. Sorry for the noise. Somebody's working on the roof. So let's go to the beginning. Here. So at 2 megahertz input frequency during a 750 second surge. Oh, that was supposed to say nanosecond. I'm sorry. Yeah. 750 nanosecond surge. So it's slightly less than a microsecond. So we see this nice sine wave, and then we see a frequency riding on top of it. Now this sine wave, I think, is the input frequency, if I'm not mistaken. 2 megahertz? See, that would be, let's see, right around here at 500, half a nanosecond would be 2 megahertz, right? Isn't a nano a mega? You know, a milli is 1,000, a micro is 1,000,000, and mega. Well, a mega is the opposite direction, so you went kilo to mega. No, I'm wrong. It should be microseconds. Oh, no, right. It's half a microsecond. Right. So at this point here, at 500 nanoseconds, it's half a microsecond, which is equivalent to 2 megahertz. So this is the 2 megahertz sine wave input, okay? But then we got this other frequency coming. Where's this coming from, right? And it's escalating. It's riding as a carrier, piggyback, on top of this 2 megahertz frequency. It's smaller amplitude. You know, this is a much bigger amplitude. This is, what is this? This is, looks like 600 picovolts. Right, these are volts. Now, I call it rotor here, but this is the transfer coil. So we get these little sine waves, but they're triangular because the poor simulator can't catch up, you know. And, whoops. And so this is a 3/4 of a microsecond window. And then now we come to about the same. No. Oh, this is less. Oh, it shows it forming better. Yeah. Anyway. So now we go to 800 nanoseconds instead of 700 or 750. And we see it ironed out. On this curve, it's ironed out a bit because we see it rising here. See, so this is going to be the rise, the surge. So with the rise of frequency comes the rise of voltage. Uh-oh. Well, not quite. So here's the beginning sine wave. But it's rising in the sense that it's, oh, I see. It's going to be a higher sine wave. So we're adding voltage to the base voltage, you know, so we've got the sine wave, that's the base wave, but we're adding voltage to it because we're adding this carrier frequency on top of it. So it's benefiting from the carrier frequency riding piggyback, increasing its frequency, is adding its added voltage or energy, potential energy, to, in the form of increased frequency, to the voltage energy value of the carrier wave. And as it does so, it keeps getting more and more rapid, and now it turns into Gabriels' trumpet. If you look that up on Wikipedia, it's a great article on Gabriels' trumpet. The surface area of Gabriels' trumpet relative to the volume. It's a fascinating subject, and it has to do with infinite mirrors and whatnot. So as we pan out over a longer duration, this is 20 microseconds, it turns into Gabriels' trumpet. And now we've got our hyperbolic surge. So, see, that's the progression as it goes from top to bottom. It's a fascinating topic how this thing develops. You know, it's really fascinating how it develops, starting with 700 nanosecond window to 750, and then it goes to 800, and then we get to 10 microsecond, and then we go to 20 microseconds, and then 50. And so you see it keeps getting tighter and tighter because it's escalating. The curve keeps getting steeper and steeper. So it's growing at an exponential rate. That's pretty obvious. And now this says, oops, it's stopped. Because that's why I don't do 2 megahertz, because I can't carry it long enough. I usually carry it to 1.35 megahertz because that's my limit. And so it breaks down at 58 microseconds, and I get this internal time step too small and transient analysis error message, and the whole thing is bottomed out. So this is really a fascinating topic as far as I'm concerned. This is the rotor. Yeah, this is the rotor. Oh, isn't that pretty colors? I love it when I do it this way. Now this, I'm coming in close for a closer view. 100 nanosecond time step. No. Oh, 40 milliseconds. Well, what is this 100 nanosecond time step? What's that all about? It's 40 milliseconds. I don't know. Oh, I was changing the time step in the simulator to see if I could bypass the error message, and of course it failed. It never worked. You know, they were complaining to me on Stack Exchange, and I was trying to accommodate them, and it never worked. So here's the C1. Now C1 is alongside the... No, it can't be alongside the spark gap. How can that be? Oh no, yeah, right, C1. Every time in each schematic I number it differently. So C1 is the one in question that's increasing the frequency. And so we go back to here. Here. So this is C1, and it plateaus. And this is where it starts, the wedge-shaped staccatos start to form. Well, they drop off because the spark gap is doing its job and releasing the circuit from a constant exponential surge, so that it doesn't, blow up, so that it doesn't turn into, it's doing this instead of doing this, instead of doing this. So let's go back to the other one. Get away from this. Here we go. So at least I still don't know why the voltage separates from the amperage, but at least now I know how the surge develops. Despite the fact that you would think the separation between voltage and amperage is a causative factor, but maybe not. Maybe it's merely an effect rather than a cause. It's one of various side effects, such as the surge itself is a side effect. Sorry for the noise again. It's roof day. Scrape. I'm in the dentist's office. See, he's working on my teeth while I speak to you. the teeth cleaning gal is cleaning my teeth. Scrape. They probably do need teeth cleaning. So they're cleaning the roof. Okay, so I'm not going to repeat myself, but maybe for emphasis. So let's recap. The diodes are taking an AC input from the sine wave generator and feeding a DC to the capacitor here. And it builds up voltage, and it starts to beyond what it normally can hold. And it starts to vibrate because it's trying to release it against the diode's better judgment. Its judgment and they are fighting with each other because they're saying, no, you don't get to release, and the capacitor says, hey, I'm ready to release. And so it starts to oscillate regardless of the fact of whether or not it's allowed to. And so it starts to oscillate, and because its voltage keeps going up, it oscillates faster and faster because we're squeezing it. So naturally, it's going to oscillate faster as we continue to squeeze it. And it would continue to oscillate faster and faster, if not without limit, if not for the spark gap eventually firing and releasing this poor capacitor from an increase of voltage. So instead of continually increasing, it plateaus, more or less, as we've seen already. And I'm sorry. I have to keep saying I'm sorry because that's all I can do. I had to say this. When I have the thought, if I don't say it right away, it's gone. It's history. I got short-term memory. For all my intuitive ability of appearing to be all-knowing, I retain absolutely nothing. Let me tell you, I will forget everything I tell you. That's why I make these videos as notes to whomever. I never watch them again, usually. Almost never. A little respite. Oh, here he goes again. Yeah, he's doing his job. Work harder. Make more noise. Okay, so that's why we have an increase of frequency. And of course, when you have frequency, you have potential energy. I've seen it somewhere on Wikipedia that frequency and potential energy are one and the same. So we're building up potential energy here, which, when it spills out back into the circuit, converts into kinetic energy, which is great, especially down over here. They can use it, these coils. But why anything else is going on, I don't know. But at least we're getting somewhere. Step by step, we're solving how this circuit works, and the whole intention was to convert it into monetary policy. But I think I've already covered that in a prior one, micro crypto network currency network. And the noise is really annoying, so I'm not going to try to speak over it any further. So you got that idea, and I hope you enjoyed this video despite the noise. Sorry about that. Next video won't have that noise. To refresh everyone's memory, in case you may have forgotten or didn't know in the first place, I forget the particulars, but in general, when frequency goes up, amplitude goes down. Whether the amplitude is with regard to wattage, overall power, or whether it's in regard more specifically to either voltage or amperage or some proportional relationship of either. Regardless, amplitude in general of something, some area of the energy value has to be compensated. It's going to be at the cost of energy when the frequency goes up, but that's under normal circumstances. So they have an inverse relationship under normal circumstances, but this is not a normal circumstance. So as I've stated before, and I just wanted to add this little last thought, the circuit demands that the amperage and the voltage rise at the same rate. So if the increase of frequency and its subsequent rise of overall reactive power is going to be at a cost of the reactive power, it sure don't exhibit that, because the reactive power, it keeps going up along with the frequency. And I don't see any inverse relationship going on at all. So that might be why this set of 5 solenoid coils are so important, is to make sure that the rise of frequency instigated by this little puny little teeny-weeny capacitor is not at the cost of amplitude. It's not at the cost of anything. Now again, that goes into the nature of reactive power, something I don't understand really at all. I just look at things generically, and then in time I get to figure out particulars or learn about the particulars, usually from other people, but sometimes from within myself. It comes to me, aha. But generally I take a top-down approach when I want to analyze something, because I have no formal training. I have to take a top-down approach. I have no other approach to take. And that, of course, affords me a broad view, and I don't get lost in details, and I don't get lost in programming or brainwashing that a formal education would have provided. Instead, I come at it raw, totally unacquainted with the subject matter, and I start out vague and fuzzy and ambiguous and confusing, and then over time it gets a little sharper image of what it is I'm looking at. So that's what I'm looking at here. I'm looking at a guarantee that the frequency is going to raise in this circuit, not at the cost of its energy rise. It's going to rise not inversely to the energy, but directly to the energy. They're both going to raise at the same time, because the amperage is going to be ensured to rise congruent with the rise of voltage, and that's probably has something to do with no cost involved. If a frequency raises usually at the cost of overall energy, I'll bet you it's at the cost of the amperage more so than the voltage. Because hey, what did Heaviside look at? The Ferranti problem is the magnetism is the first thing to go. When you lengthen a piece of wire, such as what happened in the late 1800s with the transatlantic cable problem, that Ferranti and others thought, well, let's just throw more voltage at it, brute force. So I'm guessing it's the magnetism, the current, that's the cost of a rise of frequency. That's my guess. Now, if we took it to the transatlantic problem, that was a DC situation, so we can't really use that, can we, as a analog for why, if the magnetism was disappearing, does that mean the frequency went up? Yeah. You know, oh my God, you know why? Because they got static noise at the other end. Now, it did take longer for the signal to reach them, but that's insofar as the combination of magnetic field and dielectric field, or the electrostatic if you prefer, or the electric field if you prefer, running down the perimeter and the interior of the cable. Because that's the only way to get a telegraph signal or any kind of electrical signal, is so long as both the magnetic field and the electric field coincide, both at the sender's end of that transatlantic cable as well as the receiver's end. But if the magnetic field should dissipate too rapidly, you don't get clicks, dots, and dashes out the other end. You get something closer to noise, if anything, because now the environment is going to have a greater impact on that cable than the signal that it carries. And what's the environment? Background noise. And that's what they got out of it, was background noise. Because the cable is acting now as an aerial in which the environmental input is superior or dominant over the signal that it used to carry. So the signal faded, and what you're left with is a big, huge, humongous aerial picking up background noise from the environment. So that's where the noise came from. It wasn't produced by the cable, it just was produced by the environment and picked up by the cable. So it's because the magnetic field disappeared. A component of the signal just disappeared. So let me remember now, because I lose my train of thought so readily. So the frequency, so we didn't get, so the transatlantic cable, with the loss of the magnetism, do not get a rise of frequency necessarily, but we don't know that, do we? We'll never know, because the signal was so weak, it was as good as if it wasn't there. It was, I'm sure it was there, because nothing is zero in the real world. Only in the simulator does anything go to zero or infinity. But in the real world, it's usually a question of ratio proportions of whether or not it's balanced or extreme or somewhere in between. So it probably what happened was the magnetic field was still there, it just was so negligible. Yeah, because that's what Eric Dollard said. It took longer and longer for the signal to reach the other end, which means the magnetism was still there, but it kept diminishing over time for some odd reason, so that it took longer and longer for the signal to arrive. Strange. But it did arrive, it just took longer. So the current that exhibits, or is part and parcel to a magnetic field, that has to do with speed. Makes sense. How long does it take for the signal to arrive? Makes sense. Resistance of the cable reduces the current, making it take longer for the signal to arrive, as well as being weaker. Makes sense. So weak that the telegraph receiving key failed to pick up the dots and dashes, failed to make the clicks, because its coils were only so big, you know. They would have had to, one way to compensate would have been to create this humongous sized telegraph key at the opposite end, the receiving end. Huge coils to pick up the teeny weeny little signal that arrived and magnify it using massive coils, just like Joseph Newman's device does. It magnifies stuff because it magnifies voltage because it has such a humongous coil. And a telegraph key is basically a coil, a solenoid coil. So that when this coil energizes, the key engages and gives you a sound, and when the coil relaxes, de-energizes, it relaxes the key and it releases the key and it pops back up again. So every time the coil energizes, the key comes down, plunges on the clapper, and makes a sound. So the coil has to have a chance, it has to have adequate duration to energize and de-energize so that you can hear the dots and dashes that are being sent and hopefully received. So it's really a question of the size of that solenoid coil too, not just a question of Ferrante, let's throw more massive voltage at the sender's end so that they can get the signal at the receiver's end. They could have solved it a different way, but they didn't. They could have, but see, now what is that? When you increase the size of the little solenoid coil at the telegraph key receiving end, you're increasing the magnetic reception to make up for the lack of magnetic transmittance along the entire length of that transatlantic cable. So it all comes down to magnetism anyway, one way or another. Either sending it along the whole length or receiving it, boosting it at the receiving end. They couldn't sink coils apparently in the ocean, and they didn't figure out they didn't invent repeaters, they call them, or boosting stations, I prefer to call them, until 1956, of all things. Apparently they didn't have to. Heaviside did such a good job of solving the problem. They didn't have to. And they didn't have to make a massive receiving telegraph key at the receiving end to make up the difference for receiving such a weak signal. So anyway, that was my little aha moment that I thought, oh, I got to add this into the video. After it was almost done compiling, now I'm adding in this last little sequence. But I think it's significant because it means we're not costing anything. See, in physics, they're always saying conservation of energy, meaning if you get a gain over here, you're going to have to lose or take away from over there, and vice versa, so that everything balances out. But here we're getting this humongous outpouring of energy, seemingly coming from nowhere, without any kind of balancing taking place, which is against the conventional wisdom, and it's against accountability. Isn't that how the banking system works? Accountability. If you take money from one bank, it's got to show that it was taken from there, right? If you pay your bill, one way to check to see if the person you paid the bill to, whether or not they cashed the bill, is to look in your bank account to see if it was subtracted from your account, right? But that's not the way free energy works. The energy appears, and it doesn't seem to have disappeared from anywhere else in order to appear in front of your face. So that smacks and defies against conventional wisdom of how commerce works, the economy, and how physics works, the conservation of energy. Now, Eric Dollard likes to cite a different law. He thinks the conservation of energy is a waste of time, that it's for various reasons. I think it's a misapplication of the conservation of energy law. He likes to use is something, I believe it's called the consistency. I think it's called the energy law, the law of consistency of energy or constancy of energy. I don't know. These are technicalities as far as I'm concerned. The bottom line is you get more out than what you put in. And we all know that, right? And that comes out of qfactor, quality factor. That actually addresses that. So somehow qfactor goes to infinity. That's why we're able to get an infinite surge. And I had surmised, or offered my guess estimate to the people at Stack Exchange, well, maybe the bandwidth has narrowed to a infinitely zero duration of bandwidth. In other words, it's narrowed down to the point that you don't have a bandwidth. You just have a specific frequency, and that's it. The resonant frequency of the circuit. Woohoo! So you have one frequency it operates on, and that's it. And if you can't tune to that frequency, you can forget it. Well, it's not quite that bad. It's more like a bandwidth, but it's just narrow. So it's not a flashlight circuit at any frequency sort of situation if a flashlight did run off a frequency. It's more like a narrow band of frequency that you have very narrow parameters of an upper and lower boundary to that frequency. Getting there, it's narrowing so that you get more Q factor, more quality factor, more out than in, relatively speaking. If you look up qfactor article on Wikipedia, that's what it talks about. And so that's what I got out of my interchange with the people at Stack Exchange. Well, that maybe the laws of physics allows for free energy. And so what did they do? One of them criticized or admitted, oh yeah, but what's it good for? It's just reactive power. It's lossless. In other words, you can't lose it. In other words, you can't spend it. Well, if you can't spend it, it's not good for anything. So it's got to be loss-oriented, obey the laws of thermodynamics for it to be usable. And reactive power is not usable because it's lossless. Well, Heaviside corrected that problem. and I implemented it, and so now we can spend it, provided it's at a certain rate, as I've said before. So it's an interesting situation because it flies in the face of conventional wisdom. It's making all kinds of hand gestures to, in a sense, in a roundabout way. It's as if I am saying, hey, look, this simulator is defying what you're telling me is not possible, what's not true. And so what's going on here? We got a $5,000 simulator telling me that what you're telling us is not true. The laws of economics, the laws of banking commerce requires upholding the popularistic or populist interpretation of the conservation of energy law. But here we've got a $5,000 simulator embodying a circuit telling you that you're wrong, that your fiat currency is truly a virtual reality, truly not at all conforming to reality in front of our face, physical reality. It's a fiction. Not only is it a fiat currency worth nothing, except so long as we keep spending it, it'll be worth something, but the way the economy works, the way the bankers are required to operate, double ledger, no money in circulation, zero balance at the end of business day. That in itself is weird, but they never tell us that we have no money in circulation because all the debts, balance out all the assets. All the liabilities balance out the assets. So there is no money in circulation. So there is no energy in our economy. Yet we keep running along as if there is. Why? Because it's a fiction. It's not reality. Yet here I've got a simulation done within virtual reality that's more real than the fictional reality of the economy, which possesses absolutely zero wealth. You go to your bank account, it's worthless. The only reason why you get to keep spending it is because everybody else keeps spending theirs and everything keeps moving. But, there's zero money in the economy. Since 1921 or 20 is when the Treasury Department went bankrupt. And then a year later, they switched over to completely to the Federal Reserve. They reorganized, they reincorporated or something. Of course, the Federal Reserve was the cause of them becoming bankrupt, but be that as it may, that's a different story and not germane to this video. The point is, we have no money in circulation. It's totally a fiction, yet we take it to be real because it obeys the conventional wisdom of the laws of thermodynamics, then conservation law, yada yada. Yet here I've got a virtual reality that's more real than the so-called realism of our economy. Can you beat that? I mean, in terms of ironies and paradoxes, I don't think it gets much better than that. in terms of social ironies and social paradoxes, it doesn't get much better than that. Now I'll compile this video and hopefully finish it already and move on with my life. Maybe do another sequel, but this one I think should be attached to this video because it's really germane to this. I think it's episode number 4, is it, or 5 that I'm forming? I think it's episode number 4, if I'm not mistaken. Let's double check. Episode number 4, aligning and splitting a surge. Right. So, yeah, pretty cool, huh? Or not so cool. Maybe it's time for you to panic if you've never heard this kind of information before. I don't know. Take your pick.